ask people to move to your seat and be prepared to listen to some excellent information. Welcome to the November meeting of the North Texas Renewable Energy Group. And we have an exciting speaker who's from the Texas 2036 organization. Jeremy is not going to talk to us about the energy future, but one of the things that you might, if you want to look into the organization a little bit more, they do have their legislative 89 agenda. All of us should be concerned about, what is it that if we're going to let these people go into session every couple of years, we should have an opinion on what they're doing and watch out for it. And that's one of the things the Texas 36 organization is doing. As I was driving out here, it's a fairly long drive from my home. There were four things that just kind of kept rumbling around. I might get back to them later, but one of them is the plank in the Texas 2036 Ledge 89 agenda, which talks about all of the above solutions for energy. And so we're probably going to hear a little bit about that. But rather than tell you what I think Jeremy's going to say, I'll go ahead and let him talk about this. We'll do a little bit of business at the end, but let's go ahead and start with the presentation. And I think that's it.
Hey, thank you. So I hope when we have all of the above on our agenda, you guys view that as a good thing. So, yeah, my name is Jeremy Mazur. I'm the Director of Infrastructure and Natural Resources Policy here at Texas 2036. If you haven't heard about us, we are a data-driven, nonpartisan policy think tank. Our North Star is to use the data and to have the data tell us about what the public policy challenges are and what the solutions are that are lasting to make our state the best place to live and work by the time of our bicentennial, which is in year 2036. I want to thank Bill and Georgianne for inviting me to be here. Thank you, too, for allowing me to join you remotely from here in Austin. If you were here right now, it would smell like brisket because I have one cooking on the pit outside. So if you see me casting a nervous glance over my shoulder, it's to make sure there's not a tree on fire. Bill asked me to share a little bit more about Texas 2036. We were founded about 10 years ago by Tom Luce, who really wanted to have more of a data-driven approach to policymaking in Austin. He thought that the conversation had gotten a little bit too partisan, and to have an organization that used data to help find the sensible middle to our policy conversation. We get our funding from different sources, including philanthropic organizations, corporations, and private donations. We don't fundraise and we're not paid to advocate for specific issues. Rather, our alignment is, what does the data say and what does the data say we can do to fix the problems or address the challenges that we see in the long run. A little bit about me. I worked in the legislature for 25 years. I started at the Sunset Commission back in 1999 after graduating from the LBJ school at the University of Texas at Austin. I do know the Longhorns were playing at 11. I worked in the Texas House of Representatives for 10 years. I was the Director of Government Relations at the Railroad Commission and the Water Development Board, and also I worked in the Senate. And a lot of my background is in the area of water and also energy. I know water is sometimes a dry subject, but energy has its own excitement as well. With regard to energy, our approach at Texas 2036 is we think that Texas can be a leader in this energy expansion. And was said earlier, this is an all of the above energy portfolio where we think that renewables, wind, solar, geothermal, battery storage, hydrogen, nuclear, carbon capture, and oil and gas can play a part in not only delivering more energy, more cleaner energy, but also help essentially fuel what we call the Texas economic miracle. So I have a couple of slides to share with you guys this morning to talk about what we've seen in terms of energy production trends. Why are we calling Texas a leader in energy expansion? And then share some data with regard to what we're seeing from a modeling project that we released with FTI earlier this year. So it's a small group, I gather, and it's a Saturday morning. Normally, I would wear a coat and tie, but it's Saturday morning, and I'm smoking something on a grill. Uh, I say that to it's like if you guys have questions or if you have a comment while I'm going through the presentation, let's go ahead and do it. I'd rather it's funner and a little bit more easier to have a conversation and field questions as we're going along. So please don't be shy to put a question in the chat. I can see it on my Zoom, or raise your hand or scream out loud, and we'll get there. Does that sound fair? So what I'd like to do is talk about what does the data say Texas is doing with regard to energy generation. I think it's important to look at the data we're seeing about wind, solar, and oil and gas production and generation in the state. The wind story in Texas is phenomenal. And over the past 10 years, between 2014 and 2023, the amount of electricity generated by wind has increased from over 40,000 megawatt hours to close to 120,000 megawatt hours, according to the U.S. Energy Information Administration. While Texas's wind generation has nearly tripled, as you can see on this graph, total U.S. wind generation actually grew at a lesser rate. And Texas wind generation has slowly marched from accounting for towards a greater share of American domestic wind power. For comparison, 10 years ago, Texas wind power equaled roughly 22% of all its wind generation. And last year, Texas generated approximately 28% of all US wind generation. The other thing we're seeing is that Texas is a leader when it comes to overall wind generation. We generate more wind power here than any of the other top 10 wind generating states, including Oklahoma, Iowa, Kansas, where Dorothy from the Wizard of Oz is famously from, New Mexico, Minnesota, and California, to name a few. No, moreover, as domestic wind generation expanded over the past decade, the rate of wind generation growth in Texas accounted for nearly 33% of the nation's increase. The y-axis here shows you how much our generation has grown over the past decade. And not only do we generate more wind power compared to the top 10 peer states, but the rate of wind generation growth, how much more wind is coming online, has really accelerated and blossomed in Texas compared to the other states. The same story is also true for solar generation. So solar eclipses notwithstanding, Texas utility scale solar generation has really skyrocketed over the past decade. In 2013, solar power generated about 282,000 annual megawatt hours in Texas. Last year, solar power generated over 27,000 megawatt hours, and this is a 9,705% increase over the past decade, nearly a 10,000% increase. And I had to triple check that number. It's so extraordinary. For comparison, total US utility scale solar power generation has just increased by 930% over the past decade. So we're seeing a rapid increase in solar generation in Texas compared to the US. What's also interesting is that Texas' share of US solar generation has increased. Back in 2014, Texas accounted for about 1.4%, again, 1.4% of US solar generation. And as of over the past year, it's grown to be about 17%. What's interesting too is that Texas, has seen extraordinary growth in solar generation, but the real leader here is the Golden State on the West Coast, California. Our sun, the Lone Star, is certainly being eclipsed by the California Bear. Trying to work with some metaphors here. But for comparison, last year, California generated about over 40,000 megawatt hours in utility scale solar, the most of any of the top 10 solar generating states. And moreover, California accounts for nearly 24% of of the United States increase in solar generation over the past decade. You're still seeing aggressive increases in solar generation in Texas compared to the other 8 peer states, including Sunrich, Florida, North Carolina, Nevada, and Georgia. So I mean, even if I say this to say, like, Texas does stand on its own as being one of the leaders in solar generation. So I think it's important that when we talk about renewables, we also have to talk about hydrocarbons and what's going on there. Some folks would say that, well, if we're seeing more wind, if we're seeing more solar, does that mean that we're going to be seeing less with regard to oil and gas production and growth? I'm going to show you some charts, and I know who I'm talking to. It's the North Texas Renewable Energy Group. So bear with me. I think it's important to point out, what we're seeing with regard to oil and gas production.
Hey, Jeremy.
Yes, sir.
Hey, this is Larry. A quick question on the solar chart that you were showing, previous chart. Did that include the megawatt hours generated by behind the meter solar, or was that just utility scale?
Great question, Larry. This is generally utility scale.
Okay, because I knew Texas was catching up on the utility scale, but quite far behind, still on the behind the meter. So that's why I was asking. Thanks.
Yeah, and this is like your utility scale generation. But you're totally right that behind the meter distributed generation is also pretty key. Thanks for asking that, Larry. Good to see you this morning. So when we talk about oil production, interestingly, over the past decade, oil production has increased both in the United States as a whole and in Texas. Last year and even this year, we're seeing record-breaking levels of oil production in Texas. Moreover, between 2014 and 2023, the state's oil production increased by 73% over the past decade. In the meantime, domestic American oil production increased by just 47%. Of course, a lot of this production growth we're seeing in oil production comes from Texas. For comparison, in 2014, Texas accounted for about 36% of all domestic oil production. As of now, we account for about 42% of all domestic oil generation. The other thing is, like, when we look at comparing Texas with the top 10 oil producing states in the country, Texas not only produces the greatest volume of oil, but also the greatest increase in production, contributing to the nation's overall production increase. Moreover, over the past decade, 3 of the nation's top 10 oil producing states, including Louisiana, Alaska, and California, actually saw production declines. But still, what you saw in Texas was not only record-breaking oil production, but also record-breaking increases in the rate of production as a percentage of overall national production. The same is actually true for natural gas. Is that 2023 and 2024 are also record-breaking years for the state's natural gas production. Over the past decade, our natural gas generation has increased by about 43%. But over the same time, the United States overall natural gas production has increased by 45%. You'll be surprised where a lot of that production increase is coming from when we get to the next slide. But basically, over the past decade, Texas's share of overall natural gas production of U.S. total has hovered between 27 and 28%. So of all the gas generated in the United States, about 27-28% of it comes from the Texas fields in the Eagle Ford, Haynesville Shale, and the Permian Basin. And this is the interesting thing I was talking to you about. Like, not only as I said, we produce the most natural gas out of any of the other states, and there's been a significant increase in natural gas growth production in Texas. Interestingly, the greatest rate of natural gas production growth has been coming out of the Marcellus Shale in Pennsylvania. So there's a lot more aggressive natural gas production and development going on in Pennsylvania compared to Texas. But still, Texas, we see the highest level of overall natural gas generation. So I think that's some important data to share to do some table setting here, to talk about what are we seeing in terms of renewable deployment and development in Texas and in the United States. But also, I think it's important to acknowledge what we're seeing with regard to oil and gas production. What I wanted to share with you as so earlier this year, we released a project which we call the Texas Energy Futures Project. And we did this because we think, our state's economy clearly closely aligns with the energy industry, not just oil and gas, but energy as a whole. So that includes renewables, the emerging hydrogen sector, the emerging discussion on carbon capture, as well as nuclear. And we want to know how the state's pursuit of different energy futures or pathways what kind of bearing would that have on the state's economy in terms of GDP, state and local tax revenues, and jobs as well. We also wanted to ask, what does this mean for our emissions profile? I mean, do these different pathways increase overall emissions? Do they decrease emissions, hold steady, and so forth? And so we developed, as I have on the slide here, what we think are 4 practical, viable energy future scenarios for analysis. And as I said, what we look at here is how much energy is being produced, what are the economic outcomes, and of course, what are we seeing in terms of the state's emissions profile? We did this, and this data is available online. I'll share it with you guys later. We can go explore our models and the data and all of the key underlying assumptions beneath them to provide state policymakers and practitioners with some data-driven insights about what the state's energy system, which is really an energy market, can do given certain assumptions about energy technology cost improvements over time and the rate of energy technology efficiency improvements over time. And I should also say that we partnered with FTI, which is a consulting firm in developing these projects and in developing these models for this project. So here are the 4 models that we developed. The first is what we call the status quo, a business as usual future. The key thing in the status quo scenario is that we assume moderate technology adoption and advances in cost improvements for all energy generation sources, including renewables, oil and gas extraction and utilization, carbon capture, and hydrogen. So what we're basically assuming is that the costs of all energy technologies improve at a moderate rate, and the technology efficiencies themselves, which are mapped out by the National Renewable Energy Laboratory, also improve on a moderate rate. A couple other things that we include in the status quo scenario and the other scenarios is that we model electric load, also known as electric demand, with the energy service demand within the ERCOT forecast. We also include the assumption that the minimum share of new vehicles, again, new vehicles that are electric vehicles or hybrids or plug-in hybrids, reaches about 40.5% by year 2035. And we also assume different discount rates for different types of energy industries within these scenarios. In the status quo scenario, we assume a 5% discount rate for renewables and a 5.5% discount rate for fossil fuels. I saw something in the chat, but okay, we're good. The other scenario that we have is what we call advanced fossil.
Jeremy,
and in this one,
just for everyone here might believe that they can expand CCUS, and I'll bet you can too. But before anybody reads your 5 words in a row there, the U is in the acronym for utilization. Underground storage is a proposed solution, probably even a Texas attractive solution, but not the U in the normal acronym.
That's fair. That's right. I mean, when I've been a part of a lot of CCUS, sometimes CCS discussions in the Capitol, and there's very good discussion going on. Like, are we just going to take the carbon and pump it underground, or are we going to utilize it? I think that's a fair question. Ask me again about CCUS or CCS at the end, because I don't really have any slides that talk what we see in terms of CCUS delivery. But there was some remarkable findings. So the second scenario we have is what we call advanced fossil. And here we assume more aggressive cost and performance improvements in the hydrocarbon space, where we see cost improvements in oil and gas production and technological efficiency improvements in oil and gas production, as well as with hydrogen and carbon capture technologies. We have renewables in the advanced fossil scenario, as you'll see, but the assumption there is that the energy technologies and the costs improve at a moderate rate. And so what we're balancing here is like we're assuming the hydrocarbon technologies and costs improve at a more aggressive rate, but renewables still improve at a more moderate rate cost curve. The energy transition scenario actually flips that, where we assume that there's more aggressive cost and performance assumptions for renewable energy capacity, energy storage, and so forth. You still have oil and gas production and generation within the energy transition, but those costs and technological efficiencies improve on a moderate trajectory. And then lastly, we have the energy expansion scenario. And what we do here is we assume that every single energy technology in Texas, both the technology improves and the cost efficiencies improve on a more aggressive pathway. What we like about these scenarios is that we're not modeling here how to reach certain policy objectives by a time certain. And what I mean by that, these scenarios don't provide a roadmap on how to get to net zero by 2050, how to implement a nuclear or nuclear or hydrogen economy by 2035. Rather, what these scenarios do is that we're making certain assumptions about energy technology cost improvements and energy technology efficiency improvements over time, and seeing how these improvements affect the state's energy system, which is essentially an energy market. So that leads me to one of my key disclaimers, is that these are descriptive models. We're going to describe what we think the state's energy system, which again is really market driven, will do given these assumptions. These are not prescriptive models. And I'm saying that almost as a warning, like, there's going to be some things you're probably going to see here that are encouraging, especially since this is a renewable energy group and you're looking to see what can happen with renewable energy. There's also going to be some things that you'll be like, why isn't there more of this? Or why is this happening? So, I mean, and these results that you're seeing are not necessarily because we want them or the model wants them to be that way, but rather it's showing how the state's energy system, which is a market, will behave given these certain assumptions. This slide goes into a little bit more detail about how these scenario models are designed. There are certain inputs that we put into this times model, which is an energy model, such as energy production data from the U.S. Energy Information Administration, levelized cost of energy, assumptions about energy technology costs and efficiency improvements over time from the National Renewable Energy Laboratory. Those data go into this times model, which is an energy model that works to select the least cost energy generated over time. We like using this model because generally the energy that's oftentimes produced is the energy that's going to be bought, and typically in the open market, consumers are looking for what's the cheaper form of energy. The output from times, which include energy production, prices, air quality, all that output from the times model goes into this other model called REMI. And REMI is an economic model that then in turn spits out how these changes in the energy system and these outputs from the energy system, given those certain assumptions, affects the state's economy in terms of GDP, jobs, and state and local tax revenues. So there's essentially our models are two models in one. And I apologize if my explanation is confusing, but the way I like to summarize it is that we're using two models, one that provides output about what the state's energy system will do, that informs an economic model that describes what the state's economy will do. And so that, we think, gives us a clearer picture of the relationship between both the energy system and our state economy.
I have a question.
Of course.
I see a lot of things about generation, production. I see zero about consumption or delivery. So this whole description model seems to be all around production and maybe assumptions that the consumption will be going up at the current rate or something. Can you talk about that? And also delivery. There's zero about delivery or location of where the production is or where the delivery is, where the consumption is.
Okay, so Bill, I'm gonna have some slides that's gonna talk about consumption. So give
Okay.
give me a couple minutes on that.
Okay.
The two other points that you made are, yes, these models don't necessarily say where the transmission needs to be or has to go. And that's a big issue. I mean, the models are basically assuming that the transmission infrastructure will be built in order to deliver the energy to the market. The second thing that you mentioned is like it doesn't necessarily describe where the generation will be. Somewhat, there are, when you go into our regional um, descriptions, that I'm not going to go into that today. I think it does describe what you could be seeing in terms of output from certain regions. But this slide I describe here what the modeled results are. I mean, we look at total energy production, what we see in terms of electric generation, light duty and heavy duty vehicle fleet composition, of course, emissions. And then on the economic level, we get some data with regard to GDP and job growth and state and local tax revenues. The data on our website, and I'll share that link with you later, provides not only like a statewide snapshot, but also insights with regard to what we see in the 12 economic regions across the state, from the South Texas region that includes the Rio Grande Valley all the way up to the Dallas Metroplex. So that's what we have with modeled results. What I'll share with you this morning are essentially 4 areas of modeled results. Like one, what do we see in overall energy production? 2, what do we see in electric generation? 3, let's look at the changes, the radical changes actually in the state's transportation and vehicle fleet. 4, we'll look at emissions. And then 5, I'm going to throw a surprise one in on you. We're going to talk about the economic results in terms of jobs and GDP. So let's look at the high level energy production results. And what we see across all 4 scenarios is that there's going to be an increase in energy production in Texas between now and 2025. So the y-axis is for petajoules. And keep in mind that a barrel of oil and a cubic foot of natural gas is more energy dense than wind or solar generation. And so if you're to try to provide an apples to apples comparison of the energy density of wind, solar, oil, coal, and natural gas, I mean, it's just like that's why you see these large contributions coming from natural gas and oil. But what we do see here are a couple interesting trends in terms of overall energy production. One, by and large, we see that oil and natural gas production does increase. Coal production, which is that black line in the middle, does decrease. Again, and I'll say this again later on, like if the models thought that coal would be the more economically viable or feasible production source, they would have picked coal, but they didn't. But we also see relatively substantive increases in wind and solar generation in Texas. So we have all this energy that'll be produced and generated in Texas. It's going to go one of 2 places. One, it's either going to be exported over to domestic or international markets, or 2, it'll be consumed in state. And so,
and Jeremy, before you go on, and I think you're exactly where my next question was going to be, and it's kind of a ancillary to what Bill just brought up. If you look at electricity, for example, we know that about 10% of it is going to get exported over the private transmission lines that we've got into New Mexico or the country of Mexico. The DC ties don't count for really anything on that export, but the other fuel types are getting exported. So trying to tie Texas production, you can talk about consumption, but with electricity, we know at least 90 some odd % of the consumption is local. For all these other energy types, it's probably far less than, I don't know the percentage, but it's, barely double digit percentages.
In terms
Um,
of local consumption.
right, right. So
Yeah.
again, trying to tie it to what it's a confound when you try to answer Bill's question about, well, we didn't talk about efficiency, we didn't talk about transmission or distribution. Yes, we can talk about it, but you have to understand that if you're looking at Texas, you can either put a wall around the edge of it and say, okay, production and consumption within the state, or you can talk about, well, wait a minute, a lot of it's going elsewhere. And that gets into the whole scope 1, scope 2, scope 3 emissions problems, et cetera. It is a confound in the way that you're presenting here. I just wanted to point that out.
A compound or a confound?
Confound.
Okay.
Yeah, hi, and Jeremy, hi, this is Larry again. And I know that this is kind of beyond the scope, but maybe for a future conversation, there's a lot of discussion now about when you're doing an energy transition, primary energy, as we've seen in the Sankey charts, let's say in the two largest ones here, natural gas and oil, currently like 2/3 of that dense energy is wasted. And so, the challenge is, how do you over time, because, when you look at this, it would say, hey, we're never going to replace natural gas and oil because there's just so much more. But somehow at some point we have to help people realize that, of all that's produced, 2/3 of it's wasted, whereas the wind and solar numbers are pretty much what you show on the chart. So, I understand how it's done here, but that's kind of a future conversation. And I've seen more and more debates popping up about that, because even now you hear, well, fossil fuels are 80% of our primary energy, so it'll never be replaced. But we forget to mention that of that 80%, 2/3 is, goes up literally in heat and heat trapping gases. So just something maybe to think about for down the road.
And I think also what you see, I mean, for example, with natural gas, the way the market works, I mean, I think that the Texas natural gas commands a premium when it's packed up as liquefied natural gas and shipped overseas. That people pay a premium for LNG. The cheapest natural gas that's sold in the market is typically at the city gate with your local distribution company. That's your Texas Gas Service, Atmos, and Centerpoint. And so I think natural gas certainly flows uphill to money. And so part of the reason why we're seeing a lot of this natural gas production is because that there's exogenous demands in the international market and also in the domestic market for natural gas for energy purposes and even manufacturing purposes. And it's the same with oil. I mean, it's used as a refined product for oils were refined and used in multiple manufacturing processes and energy generating processes, not necessarily being used entirely in the four corners of the state of Texas, if I can say that the state has four corners, but it's certainly being packed up and shipped elsewhere for other industrial and energy related purposes.
Jeremy, I'd like to make a comment too. I want to thank Larry for what he said, but he's exactly right. Are you aware of what the Lawrence Livermore Laboratory does? And shows that 2/3 of energy that is wasted, it's not exported, it's totally wasted, not used. Only 1/3 of the energy is used. So the charts don't really correspond when you look. Wind or electricity is much more efficient than fossil fuel, much more. So you don't have to replace as much of it. It's not about exporting, it's about use of this energy. If you're interested, I really do suggest you look at Lawrence Livermore Laboratories. They have the charts on that date way back to the 1940s or 1950s up to today. And what they show, it is really shocking how much waste we have with fossil fuels, which is not true of electricity, which is solar and wind. So these charts don't represent the reality of what we need to be thinking about. And I think it's lacking information. There needs to be more information to make this more accurate.
Yeah, Glenn, I'd say that it's accurate in the sense that it's describing the production of the energy, but maybe an additional chart in the future that shows the effective use of that energy. And in the case of those those transportable fuels, natural gas and oil, you have the efficiency issue, and you also have the issue when you're looking at it at the state level, that a lot of
Right.
that is exported outside the state versus
I don't,
so there's a couple of factors there.
yeah, I don't think people really understand this, and I think it's gonna just confuse people, or they're gonna make the wrong assumptions based on just looking at this data. So this is not the type of stuff that we need to be looking at. We need to be looking at a more realistic model of what's going on. And I'm an engineer, so I tend to rely on what data says. And this is misleading us, I think.
So I have a question. So this is when you say energy production and you talk about, let's say, oil, are you talking about out the wellhead, how many cubic feet of oil is pulled up? Or because you're not talking about the energy consumption by fuel, you're talking about the energy production. And I'm assuming this has I'm assuming you're not looking at the energy required to produce it. So let's say I produced 100 joules or 100 megajoules of energy, and it took me 50 megajoules to produce that. Well, you're just counting this as 100. You're not counting it as, right? You're counting as, in other words, no matter where the energy required to do the production, you're only looking at the energy production as an economic signal. Is that correct?
It is energy production that's responsive to exogenous forces, such as what's the market? What is the market demanding, and what's being generated in response to those market signals? Again, there's been comments with regard to waste heat and waste energy. You're not going to see anything in this chart that's responsive to those two comments, because this chart that I'm trying to show to you right now just basically talks about overall energy production. When we go to the next two slides, we can talk about how this energy that's being produced and is being generated will be exported and consumed. And then from there, we can also talk about electric generation.
Okay. And this has nothing to do with oil and gas that's used for non-energy uses, right?
It does. It is also oil and gas that's generated for non-energy uses, such as.
Oh, okay. So this is the economic impact of the material you're listing there, not the energy. Yeah. Well, you say petajoules. If it's not used for energy, that kind of confounds things too. Anyway, I'll let you continue.
We're trying to provide an apples to apples comparison between the amount of oil, gas, and coal and wind and solar generated, and so that's what we're trying to do with this graph. It's hard to find another basis where you can compare the basis of a barrel of oil with a megawatt of wind.
Well, I think the point is it isn't apples to apples.
Yeah.
Correct.
Because when you generate 100 megawatt hours of electricity with solar, almost 100 megawatt hours is put to useful purpose. Whereas if you extract the energy equivalent of 100 megawatt hours of oil, if it's used as feedstock, then it's not useful energy. Or if it's used in a vehicle to transport one person in a Hummer, it's 10% efficient. So that's not apples to apples, but it is about the only way we're used to thinking about it.
Yeah.
Point taken.
Thank you, Lisa.
So the other thing we look at here is what happens with exports. And so our models are showing what we see in terms of refined product, oil, and natural gas exports, generally across all scenarios. We see an increase, specifically in natural gas exports, particularly in the advanced fossil and energy expansion scenarios, due to lower price environments for oil and gas production. And we also see increases as well as refined products, owing to increases in oil and gas production. With regard to consumption, which, and this is basically what we're talking about, consumption inside the state of Texas, we see that there's increases in refined product and natural gas consumption, but the more notable thing that we're seeing across all scenarios is that there's nearly a doubling in electric consumption, and that's going to coincide with what we see in terms of electric generation in the next sector.
Hey, Jeremy,
Yeah.
just a clarification on this one. On the natural gas, because we use natural gas now to create electricity, is this natural gas the above what's used in any electricity generation?
Actually, we're gonna get there in a couple slides. I mean,
Okay.
but to give you an answer before we get there, Larry,
Okay.
we see a lot more generation coming from wind and solar, and a declining share of natural gas and scenarios coming a declining share of natural gas fired generation coming from natural gas.
Okay. All right. Thanks.
Another question.
When we look at electric sector results, this is what we find to be pretty interesting. It's like, first we see that electric load actually doubles over the next 25 years. And this is the key point here is that the era of flat electric load growth is essentially over. And there's several reasons why we're seeing this increases in electric demand. First, in the transportation sector, as we'll get to in a little bit, we're going to see a significant increase in the number of light duty and heavy duty vehicles that are electric, that are using that are plugging in order to charge. In the residential sector, it's hard to see in this chart, I'll admit that, but you also do see a slight increase in residential electric demand. This is largely due to growing electrification of domestic appliances, like your dryers and your stoves. But also interestingly, this is also due to a forecasted increase in the number of cooling days, where warmer temperatures, especially in Texas, is going to mean that people have to run their air conditioners longer. You have an increase in industrial electric demand as more industries start to use electricity in order to generate process heat for their manufacturing processes, as well as within the commercial sector, largely due to greater electrification. Using greater electrification within the commercial sector, and this also includes the anticipated data center increase as well. The models then project what we could see in terms of installed electric capacity by fuel in order to meet these growing electric loads. In 2025, we basically see an installed capacity that roughly approximates what we see right now. We're about 55 or 50% of your generation comes from your thermal generation sources. This is your natural gas, nuclear, and coal. And the remaining portion comes from battery storage, wind, and solar.
Hey, Jeremy.
Yeah.
There was a question here. Let me turn it back to James.
Yeah, I tried to ask it earlier. Where does hydrogen fit into all this?
Hydrogen is going to show up when we get to heavy duty vehicles. We don't actually see any hydrogen on the electric generation side, because even with the cost and technology efficiency improvements, what we find is that hydrogen doesn't really emerge to be economically competitive with other generation sources.
And Jeremy, on this slide too, I know it's kind of an emerging thing, but there's a lot of potential around enhanced geothermal that would kind of show up in the other category probably right now. And then as we learn more, it'll maybe be updated or factor in down the road.
Absolutely. I mean, there is a potential for geothermal, and we've recognized that and we've supported that. But still, when the models looked at geothermal technologies and projected efficiencies according to NREL data, it didn't really project any oversized contribution from geothermal that would have materially impacted what we're seeing. That could change if there's policy interventions or market shifts that would better favor the development of geothermal energy.
Okay, thanks.
And Jeremy, one question on the last slide, but don't go back to it, just briefly. The numbers that you showed for electricity growth were those Texas or US or
That was Texas.
Okay. And the source for those?
That was from the source is from, we modeled it after the basis of our model was originally off of the ERCOT load forecast as an input. And then the models from there projected what the load demand would be given basically the economic demands. And so
okay, because I'm familiar with the ERCOT models, and your numbers seem significantly lower for the growth.
Essentially, what I want to push back and say is, like, when we released this report in this finding in February, our models were actually higher than what ERCOT had forecasted. And then when ERCOT updated their forecast after following the instructions from the legislature, ERCOT's load forecast went from 100 to 200, just to throw out a rough example. And that's because ERCOT's now using a different way of calculating what their load demands will be. And so before, basically what they're saying is, now if anyone's thinking about moving to Texas or expanding their processes in Texas, then those affidavits are now included within the forecast, even though there's no guarantee that those proposed projects or loads will necessarily come online. And so what we're seeing now with the current ERCOT load forecast is, you're right, it is significantly higher and is more significantly higher than what our models project. But there's several reasons for why it's so much higher. I'm not saying our model is correct, and I'm not saying their model is wrong, but I'm just providing the explanation for why that happened.
Well, and the reason I asked what the model was is that I wanted to launch from a position of at least agreed to somebody else's numbers. I'll throw in an anecdotal as well, though, is, it's sort of a self-fulfilling prophecy, because, there is the energy cost, energy availability, and policy will drive the amount of load from data centers and crypto. So what we have is, part of those models are, well, how do we lean into it, and how does it therefore change the future? The anecdotal piece I want to throw at you is, I'm going to throw a number out there right now that says half of the substations that are on the drawing boards right now at the major utilities are associated with those large, 50 to 200 megawatt clients, individual growth clients that we have chosen to, open the gates for in a literal sense. And so I think those aggressive growth models are pretty real, for at least what I'm seeing right now.
I hear you on that. And that's also an issue that the legislature is trying to tackle as well. And going back to this slide, I think what we see here is, when we look at the installed generating capacity by fuel between 2025 and 2035, is we see a substantive increase in solar in yellow, wind, it's kind of in that teal blue, and then battery storage. A lot of this increase is largely due to the tax credits that are being provided by the IRA, the Inflation Reduction Act. And what we see in our models is that the IRA tax incentives are an incredibly powerful tool towards bringing a lot more wind, solar, and battery storage online in Texas. After 2035, actually 2036, when the tax credits in the IRA are set to expire, you still have wind and solar generation, where you start seeing a slight uptick in natural gas generation as natural gas generation becomes a little bit more cost competitive with wind, solar, and battery storage. Two things I want to point out here before moving to the next slide is, like, first, the amount of coal-fired generation actually declines. If the models had found coal to be an economically viable generation source, then it would have picked it, but it just doesn't find that coal is going to work in terms of being a long-term electric generation source. The second issue is that the purple line here, which is probably very hard to see, that's nuclear. And a lot of folks ask me, like, why don't we see more nuclear here? Again, going back to cost, nuclear plants are very expensive to develop. I can tell you for a fact, this is an issue that the Public Utility Commission and the legislature are working to tackle right now. And the models just could not, the nuclear was not cost competitive enough compared to wind, solar, battery, and natural gas to see more nuclear development. This is an issue that I can tell you, Governor Abbott and state leadership are looking at. There's currently a committee at the Public Utility Commission that's trying to see what, if anything, the state can do to expand its nuclear capacity or nuclear fleet. But at this time, it's hard to conjecture or project what exactly will happen. I know there's probably a lot of conversations about small modular reactors, among others. But it's we all know that in order to bring these things online, it's going to require a substantive amount of either market changes or public investment.
Can I ask a question too? The cost of these new substations to support crypto or whatever, who's going to pay for that? Why should I pay for it? Or what's the model to have someone who actually uses it pay for it? And instead of driving my rates up personally, even though I don't use it.
Yeah, the models don't project like where the cost burdens will be, and again, the models don't project like how the financing would be provided for the transmission or transportation infrastructure.
Okay, just concerned.
And Anne had a question too, which I think is incredibly germane, and she asked a good question, like how will these projections shift with President Trump saying he will eliminate the IRA? That's a good question. I don't know. What we do know based on our models is that we see that the tax incentives from the IRA are an incredibly powerful driver towards bringing more wind, solar, and battery storage online. If those tax credits expire, I suspect you're still going to see substantial renewable generation and development in Texas. I mean, look at what's happened over the past 10 years in the first 4 slides that I shared with you. And this is me just going into conjecture land. I don't know if the future development of renewables would be as robust as what you're seeing right now, which describes what we can anticipate with the tax credits remaining within the financial environment.
Hi, I had a quick question as well. I was wondering if there's a significant amount of hydroelectric power generation in Texas, because I was wondering why it wasn't included in this graph.
That's included in other. Thanks for the question. That's included in other. The challenge we have in Texas is we do have some hydroelectric dams. Like we have them here in Central Texas that are administered by the Lower Colorado River Authority. It really comes down to an issue of stream flow in Texas rivers. And that we're a very drought-prone state, and surface water stream flow is sometimes just not substantive enough to sustain hydroelectric generation or increased hydroelectric generation, unlike what we see in the Pacific Northwest, where in Washington State and I think also in California, they have enough water, especially in Washington State, to support substantial hydroelectric generation. I like that question. I work on water policy a lot, so thank you. Then moving next to what we see in terms of like installed electric mix by fuel. Again, when I said earlier, what we see in 2025 is basically installed mix that approximates what we see right now. We're about 50 to 55% is coming from your thermal sources, your coal, natural gas, and nuclear, and the remaining 35% comes from your renewable generation. What's really fascinating about this slide, though, is like you can see how powerful the tax credit is in terms of not only expanding the generation mix, but also incenting a lot more wind and solar to come online. And then it's after 2040, across all 4 scenarios, where you start to see basically this 30-60 mix holding, where 30% of your generation, 35-65 mix holding, where according to the models, about 35% of your generation comes from thermal generation sources. The remainder comes from wind, solar, and battery storage.
I'm surprised that battery storage isn't increasing faster, since it's increasing very fast this year. Do you think it's going to slow down?
It is increasing very fast. It's the question. I mean, I think there's still questions with regard to and the models do take into account the data from the National Renewable Energy Laboratory, like what we can anticipate in terms of efficiency and cost improvements over time for battery storage. I think what you're seeing is like, I mean, batteries are certainly going to increase, but they're not just projecting that they're going to increase to the point where they're going to be able to like provide consistently reliable, dispatchable generation. The other thing that we have in our models, which is interesting too, is that when we look at the wholesale electric prices across all 4 scenarios, it's like, again, thanks to the incentives from the tax credits in the IRA, between now and 2035, we actually see your wholesale electric prices decrease, especially within the energy transition and energy expansion scenarios that have a greater deployment of wind and solar and battery storage within their generating portfolio. You still see decreases in the status quo and the advanced fossil, but the absence of greater renewable penetration in both those scenarios actually yields slightly higher wholesale prices in the long run. And then after 2035, when those tax credits expire, the models project that you're probably going to have greater natural gas generation being developed. And so that's why you're seeing this, I would say, duck back, where you see these increases in wholesale electric prices after 2035 up into 2040 and then leveling out thereafter. And then the other thing that our models have, it's not available on our website, is what they forecast would be the electrical power sector capital investments, like who's going to be investing money in what type of generation. In 2025, you're already currently in 2025, you're seeing the bulk of the capital investment going towards renewables, and especially by 2030, where the models are projecting, thanks to the IRA, and into 2035, you're seeing substantive amount of capital investment in your battery storage, wind, and solar. It's not until after 2035, when those tax credits expire, that you start to see a cost competitive environment for natural gas generation to still pick up. And then after that, between 2045 and 2050, that's where the models are showing this mix of investment between natural gas, battery, and solar. That's what we have for the electric generation side. Moving quickly over to what our models project for the transportation sector. What do we see in terms of light duty and heavy duty fleet development and composition? What's interesting to us is that we see across all 4 scenarios that, one, there's going to be more vehicles on Texas roads and highways. Intuitively obvious with a growing state and a growing economy. The fascinating thing here is that the models are projecting that both the cost and the efficiency of light-duty electric or hybrid light-duty vehicles is going to improve over time, so that EVs and hybrids become a cost-competitive alternative to internal combustion engine vehicles. And so what we're seeing is that, and actually this is an interesting story. When I told you that at the very beginning, we did not tell the models to achieve any desired results at the end, just basically to take these front-end assumptions and to project what's going to happen with the state's energy market and system, given these front-end assumptions. The models actually projected basically across the board that by 2050, every light-duty vehicle would be electric or hybrid. This is the one point where we said, we got to stop here because it's Texas. There's going to be the people that want their diesel trucks or their internal combustion engine SUVs. And so we did put a 10% cap at the end on ICEs, but still the models are projecting that even when we had to put that artificial cap on internal combustion engine vehicles, the model's still projecting that over time, we're going to see a substantive uptake of electric and hybrid vehicles. And then when we also look at what the fuel consumption is, I mean, this is pretty impressive because we're seeing that the consumptive efficiency of the state's light-duty vehicle fleet improves over time, where there's going to be less gasoline consumed and greater electricity, but this yields greater efficiency over time on a petajoule basis, where across all 4 scenarios, again, we're seeing the energy used for powering our light duty vehicle fleet decrease.
Can I ask a question here real quick?
Of course.
I guess from looking at this, and I always thought the transition right to battery would be more like a 10, 15 year, but from what you're telling me here, it looks like it's going to be like from 2050 before it comes back. And so I'm looking at, say, if you're buying now a car, electric, you want an electric car versus, you know, a combustion engine, it's still going to be only maybe 10 years, or I guess in your other graph, still like 10 years before even it gets even near, you know, not 2035 before it gets near where half the cars are battery or not. So I guess would you, if you were buying a car, would you buy a battery operated car? Or would you just wait, say, well, you know, I get gas powered and then I'll further down the road, I might get a battery, or does it matter at this point?
Are you asking me personally, or just what the models are saying?
I guess there's like the trend's going slower than I would have thought, you know, a year ago from now. But yeah, so I'm just thinking, you know, when I'm looking at purchasing the car, I guess the best thing is maybe get a battery powered, but I'm not so sure now looking at this. So it looks like I have still more time before, you know, we transition out of it. So
well, I think it's a good question, Jim. I mean, when we first started developing these models with FTI a year and a half ago, I think, you know, it was a far more bullish environment for electric battery powered vehicles. And it's unmistakable to say that, you know, that bullish sentiment has certainly ebbed. But I think at the same time, what we're seeing in the market is, one, the efficiencies of these vehicles is improving. They're getting over the range anxiety, bells and whistles that people like. And then at the same time, too, is we're seeing that the costs of these vehicles are also coming down. And so what the models are projecting is that, you know, given the assumptions about these cost improvements and these efficiency improvements with these vehicles over time, they're going to be a more cost-effective consumer alternative. And so I think what they're saying is like, yes, you're in 10, 15 years, you're likely going to see a greater uptake in electric vehicles.
But Jeremy, this isn't new car sales. This is total mix, right?
Correct.
So, you know, if the new car sales were 50% electric, you know, that would still take quite a few years to actually penetrate and show up as a larger number on this graph. So
I mean, the only way you can get rid of the ICEs is wait for them to break down, crash, or to mandate that they be taken off the road. And the latter is just like politically unfeasible.
Yeah, and like in Norway, where they're doing close to 100% electric car new car sales, they still have, you know, a substantial number of ICE vehicles on the road just because they're out there for a while.
And again, Larry, that's why we had to, when the models went to 100% EVs, we had to step in and say, it's not going to be right. We had to, we suspect there would still be a Texas market for ICE vehicles at the end of the day.
The hobbyist, right?
Yeah, the hobbyist.
No, I'm just kidding. Sorry.
Whatever the preferences are. And then when we look at the heavy duty vehicle fleet, and someone had asked earlier about hydrogen, where does hydrogen show up? Hydrogen essentially shows up in heavy duty trucks, where we see that in our models, hydrogen works as a bridge fuel between diesel engines and electric engines over time. And so this is where hydrogen basically works to play a role, I think largely due to the 45 Z or V tax credit that was authorized under the IRA. But again, one of the fascinating things here is, like, you know, the models are projecting that, again, the cost and technological efficiencies of these heavy duty vehicles increases over time, so that in 25 years, the heavy duty vehicles you see are either going to be electric or hydrogen.
Where does the hydrogen come from?
It doesn't specify whether or not it's blue, pink, gray, or whatever color of hydrogen. It's just like, you know, whether or not it's fueled, the vehicle itself is fueled by hydrogen.
Jeremy, on this chart, you know, again, I know the models were done back a year or so ago, but it shows kind of a surprising amount of hydrogen. Are there a lot of hydrogen heavy duty vehicles on the road now? I didn't think they were production ready yet.
I mean, when I've been talking with folks in the hydrogen industries, remember the Texas Hydrogen Alliance, they're out there, they're being developed. I think you're correct, Larry, insofar as the saturation is not as extensive as is suggested. By next year, you'll see this number of vehicle miles driven by hydrogen trucks. But I think it's fair to say that we're starting to see uptake. I mean, even
Okay.
Capital Metro, in Austin, which is the public transit authority, is looking at bringing hydrogen powered fueled vehicles into its fleet.
Okay, all right, thanks.
Do they use burn hydrogen or do they use a fuel cell and make it electric?
It's a fuel cell.
Okay.
And then almost towards the end, the one thing we want to look at is in emissions. And so again, at the very beginning, when I told you about our model, these models were descriptive, they're not prescriptive. We didn't model how to get to certain emissions targets, such as net zero by time certain. And so, generally what we see is that when we look specifically at greenhouse gas emissions, and I'm just going to share our greenhouse gas emissions findings here. There's other data that we have with regard to your criteria emissions, your SOx, NOx, and particulate matter. Is to classify it generally, what we see with greenhouse gas emissions is that we see them holding steady over time. You do see improvements in certain sectors, specifically the transportation sector in blue at the very top. You see a net decrease in greenhouse gas emissions. The same is also true with your electric power sector, the yellow at the bottom, where you see greater electrification. The greater the deployment of renewables within our generating grid decreases the emissions that we see from the electric power side. The culprits, if you want to call them that, or why we're seeing no substantive decreases in emissions, are pretty much due to your continued operation for the energy supply, which is your oil and gas production, whereas your emissions from the residential, refineries, and industrial sector largely holds constant, even as they're approaching greater use of electrification.
So on this chart, power kind of represents electricity, and energy supply is, if we go back to that production chart, because we're producing a lot of oil and gas, the emissions associated not only with producing it, but with actually burning it, is that what's captured here?
No, if you're well, I think the energy supply is from the generation of oil and natural gas. If you're talking, Larry, if you're talking about burning it as for natural gas fired generation, electric generation, that's incorporated in the electric power part, the yellow
right,
bottom.
Right. But again, because oil and natural gas are things that can be, exported, does this include those exported, the combustion of that energy supply that's exported, or just if it's
in Texas?
So if it's combusted in Texas,
or produced in Texas.
Okay.
One thing here, can I ask a question? Does this mean that controlling emissions and stuff is not going to change? It's going to be the same thing? I mean, we always talk about we want to go electric so we don't have greenhouse gas, but from your chart here, I would say it looks like that it's no matter what we do here, it's going to be same greenhouse gas emissions. So
I think what we see is when we look at what these models are telling us is that first you see emissions improvements in certain sectors. The other thing that we're going to see is that you're seeing an improvement in emissions intensity. And what I mean by that is you're going to have greater economic growth and greater population growth with less correlative emissions. But factually, and as in clear with these graphs, you basically see, I mean, just stepping back and looking at the aggregate numbers in these four scenarios that we modeled, we don't see that necessarily net decreases in emissions compared to current levels.
So we're basically doomed, right? So we're going to put out some.
But Jeremy, to that point, population differences, you know, and if we looked at per capita emissions today in Texas versus 2050, are we assuming a lot more population? So, you know, at least one positive would be the per capita emissions in Texas have gone down?
That's what I'm talking about with regard to emissions intensity, is that I mean, if you look at the overall emissions per capita or per unit of economic output, that number actually decreases, where, in other words, I mean, as opposed to, like, you know, a 2-to-1 ratio of emissions to person, it goes down to like 1-to-1 over time. So you get this improvement in emissions efficiency over time, but you still have emissions. And to be clear,
so with energy,
yeah, just I have some additional comments on this that Jeremy and I have talked about in the past that I wanted to kind of share a little bit with the group, but I'll wait till further toward the end here.
So with energy supply, you're essentially talking about petrochemical extraction.
Correct.
Emissions. And you're not assuming that they're going to be much more, that they're going to improve their technology. So you're assuming that they can't improve the technologies they're using, develop new technologies with less emissions for the extraction, or new policies?
We assume what the assumption there is that the production technology efficiencies improve over time. And so far as, like, you know, and just like the total generation, it didn't have any specific assumption there, Bill, with regard to their emissions capturing technologies.
So you're assuming no technology improvements in emission captures for, okay, that's kind of, that's pretty, it's amazing that over 25 years, they wouldn't improve their efficiencies on their ability to capture emissions.
To a certain degree, they do, because you do see, I mean, you do see increased oil and gas production over time, which is continuing with the trend over the past decade. The previous slides that I showed you that we were having, you know, greater oil and gas production, and, you know, even with that greater production, you still have these emissions, but they're just not as great as they could have been.
Okay, I'm just surprised there's not more technology improvement, but that's maybe that's the situation. Thank you.
So somebody mentioned scope earlier. So are those emissions in Texas?
Yes, that's a good question. These emissions are just entirely in Texas.
Okay, so a two-part question is, one is, have you done any comparison between your models and ERCOT's long-term system assessment? And the specific question is, I think they had some scenarios that included basically policy changes that would encourage carbon reduction. I don't see any of that here.
Yeah, it's, again, these models are descriptive, they're not prescriptive. We did not include any policy objectives or policy frameworks in this. What we did is we made certain assumptions with technology efficiencies and costs improving and seeing how the system works. If there are policy objectives, such as like with regard to like certain emissions reduction targets or things like what you're talking about with ERCOT, that's a separate model that we didn't do here.
Well, that's the point, is that ERCOT has to plan for what may or may not happen, regardless of whether it's because of policy things or not. So the fact that this doesn't include models that include changes due to policy changes means that it's kind of limited in that scope. So that's, I think, why you don't see the carbon reductions, is because that's not something you consider.
Fair enough. Thank you. Let's go to the economic results.
Hi, sorry. I have a quick question as well. So in the previous graph, I don't really understand the differences between power, energy supply, and refineries. Don't they sort of overlap? And secondly, this model is predicting that in 25 years, even with an increase in renewable energy, doesn't generating wind energy, solar energy require a lot less energy than producing coal. And this is sorry, this is predicting that the amount of energy supply would remain almost constant. I don't completely understand. Could you, or okay, yeah, emissions, sorry.
Of course.
That was
the
my
model
question too. Yeah.
project at the beginning that the amount of energy supply increases over time in terms of like, one of the first few slides we had was like, we see increases in energy production across the board in Texas, including renewables. Your question also asked, like, wasn't there overlap between energy supply, refineries, and power? Fair question. The energy supply is essentially your upstream oil and gas production. What happens, like, the generation from the wellhead, the transmission through the pipeline, when that goes into a refinery gate, where it's going to be processed into being a refined product or other material, that's a separate emissions category here. And then with regard to electrical power, again, like refining, that's a separate of this. What we're doing is we're that's also separate. So we're describing what are the emissions that we anticipate from electric power generation.
So the opportunity is, again, different from the descriptive models that you have here, is the more society could electrify things, then that could help further reduce emissions. If some of those industrial processes or refining processes could become more electrified, there's opportunities to reduce it. But again, as you pointed out, your models aren't trying to project what different policy things may or may not happen, right?
Yeah, again, these are descriptive models that show what the energy system would likely do given these energy technology and cost efficiency improvements over time. Then the last section is like when we look at economic results. Again, we wanted to do this to see how changes to the state's energy system what would that mean, not only for emissions but also what it means for the economy. And I think when you working on energy policy in the legislature, I mean, the legislature are keenly aware that there are several things that prop up the state's economy. One of them is a reliable, dependable electric grid. And they're also aware of the state's role, not only on an international basis, but also a national basis. I mean, just the amount of energy that's generated and produced here yields a lot in terms of increased manufacturing and exporting opportunities, which have a lot to do for a lot of good things for regional economies. So we looked at several factors here, and these are again available on our website, which I'll be able to share with you later. When we look at state GDP growth across all four scenarios, we see that all four scenarios do project that you're going to see an expansion in the state's economy. We'll see the GDP in the status quo, which is in the orange line at the bottom, will increase from 2.4 trillion in 2025 to about 4 trillion in 2050. But you see more aggressive GDP increases over time in the energy expansion and the advanced fossil scenarios, largely due to increased use of hydrocarbons and greater exports of oil, gas, and refined products. And so that's basically what leads to this the delta between the energy transition and the status quo and the energy expansion and advanced fossil scenarios with regard to long-term GDP growth.
I have a question about that.
Of course.
How are you calculating the GDP? Do you include medical cost of air pollution at all in this?
The GDP data comes out of the REMI model that projects how these inputs from the energy sector would affect certain various other sectors like the industrial, manufacturing, energy, and so forth. And that's what yields the aggregate GDP data from the economic model that they used. The data that you're talking about, such as healthcare costs, presumably attributable to increased health costs due to certain emissions, that's not necessarily factored in here.
Right, which could make this completely wrong. So I want to be clear that this looks like written by, well, this looks like it's designed for people that are in a corporate boardroom that don't care about the health of what's going on in the rest of the society. It's more than just what's happening in the corporate boardrooms. So I want to be clear that I think this is very distorted if you don't include healthcare, but that's my personal belief.
The other thing that we looked at too was like what.
Going to say on a related question, when you talk about greenhouse emissions, are you only talking about CO2? Or would this include, you know, like SOx and NOx and other emissions, which would pertain to health? I was just curious if any of the other emissions other than CO2 were included in REMI.
Yeah, listen, we do model what happens with the other criteria emissions, and that's what's tracked by TCQ. That is your SOx, NOx, particulate matter. Yes, we do.
So you could get to some medical correlations there with that. I mean, it's not impossible for you to calculate.
You certainly could. We didn't model that with this.
Right. And methane's probably the biggest one.
Well, not for human health.
Production. Right.
So the other thing is too, is like we looked at what the regional impacts were for GDP. And we see that in the upper right, you see how the GDP growth is distributed by region of the state. And a lot of the economic growth is principally concentrated within the Texas Triangle between DFW, Houston, and Austin, San Antonio. You still have economic growth in the other portions of the state, but a lot of that growth in the status quo is concentrated principally in the DFW and Houston regions. In the advanced fossil and energy expansion, that compares the GDP growth in other regions to the growth forecasted in the status quo. And I think that's, if it's confusing, I'm sorry about that, but it's the best we can come up with. But you see greater rates of GDP growth, not only inside the Texas Triangle, but also in West Texas and South Texas, largely owing to continued and increasing oil and gas production over time. In the energy transition in the lower right, you still have regional GDP growth, particularly in DFW, in Houston, and the Austin, San Antonio area. The growth is slightly less in the West Texas and South Texas regions, largely owing to less than that in the status quo, which still means you have economic growth in West Texas and South Texas, but it's just not as much as in the status quo, owing to lesser hydrocarbon production within that scenario. The same is also true when we look at jobs. We look at total Texas employment by scenario. We find that the expanded economic activity within the energy expansion and the advanced fossil scenarios correlates with expansion of manufacturing activity, export activity, service sector activity, among others, that leads to an increased number of jobs generated. You have jobs still growing within the status quo in the energy transition scenario, but that job growth is not as robust as that seen with the increased activity in the other two scenarios. And then the same is also true with total tax revenues, where you're having the expansion economic activity in the energy expansion and advanced fossil scenarios basically expands the state's economic tax base, your sales tax base, and also your property tax base. That in turn provides state and local governments greater revenues over time compared to the other two scenarios. Again, the other two scenarios, you have economic growth and you have you do have economic expansion, but it's not as robust as that seen in the previous two scenarios. So I know the time was supposed to be at 11:30, so I will go through our key findings. So again, as I said earlier, these are descriptive, not prescriptive models. And when we've visited with legislators and state leaders about these models, they would ask questions about what are we seeing on emissions, what are we seeing with nuclear, what are we seeing with hydrogen. These models, we think, provide insights about what's likely going to happen to those things if nothing else is done. And so the short of it is like, if there's something that you don't like, it tells you what it basically says that you certainly need to do something in order to make for that to change. A couple of a couple of the key findings that we have, which we think are pretty important with this legislature, is that first, when we look at renewables, we see that the IRA is bringing a lot of renewables to Texas, and that renewable generation growth is going to help our overall generation growth. More importantly, as we've been pointing out, is that this greater renewable generation and development is going to lower wholesale electricity prices. And in this legislature, which likes to hear about lowering the cost of business, these lower wholesale electricity prices yield greater economic opportunity. The other thing that we notice in these models is that hydrogen and carbon capture are there. We saw hydrogen emerging in the heavy vehicle fleet development, but it's not as robust as folks are wanting or talking about in the legislature. And we think the principal reason for that is you need to have more robust market frameworks for hydrogen and carbon capture to likely work. And so for carbon capture, if you really want carbon capture to work in Texas, you likely need something like a market. And also, as we talked about just a couple minutes ago, there are several sectors that have opportunities for emissions reductions, specifically the electric power and the transportation sector. As we have more EVs and a greater renewable deployment in our generating fleet, that can lower our emissions profile there. But there's still continuing challenges within other sectors if you're looking at reducing overall emissions. And then the last slide is I think is the website on here? Yes, it is. If you want to look at our scenario and our scenario data and some of our other key findings, it's available on our website at texas2036.org/energy-future. And that is it.
Thank you very much, Jeremy. By the way, we're going to publish the slide deck you sent me on our website. That's okay, right?
Yes, you can do that. Let me go ahead and Bill, I will save that for you as a PDF, so it'll translate easier to your website.
That would be much better, because that's the way we normally do that, is put it up as a PDF. That would be fantastic.
Happy
to. Hey, Bill, I got a couple of questions when you're taking questions.
And Jeremy, I'm gonna, while it's still fresh in our mind, the last two bullets on your takeaway slide.
You want me to put it back up?
Well, if you would, because
yeah,
I don't.
Yeah.
I think those are almost statements as opposed to results from the modeling, and they're both saying the same thing. With the only reason that there have been improvements for the emissions in those sectors and will continue to be. And the only reason that we don't see hydrogen and carbon capture markets evolving is because, frankly, there is a market that says if there's no cost for carbon, then everything has to float on its own, and that's the market we're modeling. So of course, if a vehicle can be efficient without it having to consider that, oh, well, wait, I'm more efficient. When I say efficient, dollars per mile, not amount of emissions. Both of those last two bullets are basically saying without a price of carbon, we are going to exercise the status quo. And the second half of the sentences are just kind of saying the same thing. Without a cost of carbon, there will be no change.
That's what I said.
Well, but it doesn't come out of the finding that those are statements. Those aren't results of your modeling.
Well, when we work with the model, these are the findings that we came up with.
It gets back to the discussion of, well, have we modeled in here a cost of carbon? Have we modeled in here a cost of other?
Is there a cost of carbon in Texas right now?
No, there isn't. The question is, by 2050, why would we model a system that didn't have any as one of the transitions of here's the enemy, and it's based solely on the economics of let's just continue burning hydrogen and hydrogen-based fuels and try to equate all other energy sources with that.
So what we did model was, again, the stated energy policies that are basically in place over the past 2 years, and seeing how those stated energy policies work given these technological and cost efficiencies. When we did those models and we saw the results with regard to carbon capture output and hydrogen output, we saw that, if you want to have hydrogen and carbon capture work, you need to create market frameworks for them to work. And so indeed, we did put the statement in there saying that as a finding.
Jeremy, this is Rosa Weinstein. I'm coming to your defense to what you've been hearing. The assumption that has been made regarding changes, especially.
We can't hear who's talking, sorry.
Yeah.
Sorry, this is Rosa Ornstein. Sorry. The changes and the assumptions about the changes in policy that
Are you heading towards the microphone? We can't hear you at all.
Sorry, this
go.
is Rosa. Sorry, this is Rosa Ornstein, and I'm coming to Jeremy's defense regarding the assumptions that are made regarding the policy changes that we would all like to see to take account of the cost of carbon and the cost to our lungs and our health of the fossil fuel generation, especially in Texas. We all need to recognize that the legislative powers that be have been in power in this state now for 30 years, and it hasn't changed. So he's projecting out 25 years from now, unless there is an actual change in the power structure in Texas, his assumptions are actually extremely reasonable to make. That's all I'm saying. We'd all like to see it, but Jeremy, you're the messenger. We're not shooting you. You just have a very educated audience here. But I just wanted to come and say the assumptions, given the realities we have all had to deal with for 30 years, are not unreasonable at all.
Yeah, and I'd like to kind of comment on that. Additionally, Texas 2036 has been very successful in all the areas that they advocate for, and they do that by, driving data and help get bipartisan action on, whether it be education issues or broadband issues or whatever. So I would like to, and I put it in the chat, they've recently with this, with their policy agenda for the upcoming legislative session, they're asking people for their inputs. So if you look at what I put in the chat, if greenhouse gas emissions are an important issue for you, which they are for me, just add that to your comment. Thank them for all the work they do, and say, please get more involved in trying to help prioritize, your efforts on greenhouse gas emissions reduction. So that's what I've put in the chat. I'd like to emphasize people do that. We're trying to do that with volunteers and other organizations as well. The other thing, because Jeremy has been kind enough to do this talk to many different groups, and some that I've set in on, I think a key takeaway that I got in conversations with him is that while those of us who are really concerned about reducing emissions, there's an opportunity in this data that basically shows electrification of transportation and expanding renewable energy are not going away. They're not enough for what we would like to see. But if given the, what Rosa was just talking about in terms of the current makeup of our, political situation across the state, if they can help drive the message that helps those legislators understand that, EVs aren't a fly-by-night, renewable energy is going to fade away. What they're showing with this data is they're real, they're here, and they're expanding. So that's a positive message that we want to kind of reinforce. And again, those of us focused on this particular issue of emissions reduction, it doesn't go far enough, but it helps reinforce that. So I'd like to thank, again, Texas 2036 for doing that. And then another question with the question that came up with health, we've got conversation with some people at the Texas Physicians for Social Responsibility. So this is a question to Texas 2036. Have you guys ever talked to that group or groups like that might be trying to factor in health modeling into your future models? Or is that something we could help push in some way?
Larry, thanks for your comments. I just want to say, like, yes, I mean, when we share these modeled results with folks, we get a lot of passionate questions. But I think you're right. We're modeling what stated energy policies do, given these energy and cost assumptions, and what you can expect. And I've been telling people, if there's things that you like here, like what you're saying about renewable generation and EV uptake, that gives you some sign about like what the markets can do. If there's things you do not like here, it really illustrates, you know, where the challenges will be and where you want to focus your efforts for change if you want that change. Your question about have I engaged with the what was it, Physicians for?
I think the one that we're going to try to talk to is called Physicians for Social Responsibility. And I think there may be, it's Texans Physicians for Social Responsibility, and it's tied around, you know, health impacts of climate. That's one of the things that they're working on. And so, you know, I know Texas 2036 works on a lot of different areas. Has there been in other areas conversations with healthcare or whatever that we could maybe find a parallel to take all this modeling work that you've done and say, how can we couple that with some healthcare modeling with a group maybe that you're already working with? So
yeah, we haven't taken this. I mean, I know the question was asked. I mean, do we take into account I think it was you who asked the question, do we take into account what emissions mean for healthcare costs and what the impact would be for GDP? We've not done that yet.
Can I
And so I guess the answer is like, no, we haven't done that. Doesn't mean.
But are there any healthcare organizations that Texas 2036 is already engaged with on other, you know, like your healthcare initiatives or education or something that you know you could partner with, or we could encourage them to partner with you?
Yeah, I think it's our health team who I work with. I mean, I know they're working on several other health initiatives. I know that's not necessarily the best answer to what you're asking, but I don't know if they're not really looking at healthcare, I think, in the lens that you're looking at it right now.
Okay. Well, we are going to try to, we're going to meet with this other group to talk about it. And so I'm going to encourage them to reach out to Texas 2036. So just FYI. Thanks.
And, you know, one thing I would like to say, like Larry, you mentioned that we've published our legislative agenda for the next legislative session. And there's several energy related things that we look to support, building on what we did last session. Last session, we worked to support, you know, several bills that were introduced that would have created better frameworks for geothermal energy development, as well as hydrogen. There were some bills on carbon capture that we engaged on. But you know, looking forward to this next legislative session, based on this data, I think one of the points that we're going to be making is that we need to make sure that Texas continues to be a leader in energy expansion. We need to look at this data to recognize what a renewable generating portfolio can deliver in terms of net generation and wholesale electricity prices. And what's important to recognize here is, like, these are data points that are going to be very critical in these new legislative sessions. And, you know, other points that we want to advocate for is we need to have a bigger conversation with regard to transmission. I've been having multiple stakeholder conversations here about, you know, what are going to be the big grid issues for the next legislative session. And I think, you know, the success of the renewable generation that's coming online hinges on being able to deliver those electrons that are generated in South Texas to outlets elsewhere in the state. And so I think transmission will be an important point.
Yeah. Just comment. I've looked at the International Monetary Fund. Now, this is not Texas, of course, but they said for North America, as part of the UN, by the way, International Monetary Fund, they said the subsidized and externalized costs. Subsidized, you can know what that is. External is things like Hurricane Helene, Hurricane Katrina, what's happening in California, et cetera.
Mhm.
And they said it was about 760 billion per year. And you divide that by the population, it turns out that roughly, I don't know what you use for the population, but it kind of came out to about $2,500 a person. Most of that is externalities. And I looked up the what the National Institute of Health and Harvard University said. Harvard said it could be as high as 886 billion for externalities on health alone due to climate change, due to carbon dioxide, climate change. So it's huge numbers, and they seem to have gotten forgotten. And I'm sure there's an impact here in Texas. Of course, this study that I looked at, it covers the entire United States, but it's shocking the amount of money is spent on this stuff, and they say there's no cost for it. There is a cost, a huge
I think
cost.
I mean, legislature is noticing that Texans are paying for extreme weather. I mean, look at 2023, where our grid set, thankfully,
Yeah,
multiple generation records owing to there being a hotter summer. On
yeah.
top of that, there are issues relating to drought. There's issues relating to flood. There's issues relating to storm surge that Texans are certainly paying for right now, and what we're
Yep.
seeing in terms
But
of higher insurance premiums.
I don't think people put a number on it.
Uh,
And when you see
yeah.
$2,500, I go, wow, geez, damn, that's a lot of money. Every one of us, $2,500. That's huge.
There's
Yeah.
a Texas 2036 has done some really good work on extreme weather with a Texas climatologist. So I'll find that and put a link in the chat as well.
Yep.
Thanks, Larry.
Yeah, I've used their information. I appreciate your information. I've used it in the past, so it is quite valuable, especially about weather.
I mean, when you looked at the previous chart we had on electric load growth, I mean, we're anticipating, one of the major drivers, and we've been saying this as well, one of the major drivers for electric load growth is hotter temperatures. Temperatures go up, thermostats go down.
Yep.
Yeah,
Well, hopefully that stay the same, supposedly, but it's still hot inside,
I hear
hotter
you.
outside.
yeah, that was a side question I had because I noticed your increase in electricity for higher temperatures. Did that factor into your model at all in terms of the ability of fossil or basically thermal power plants to generate electricity when the water that they're bringing in to cool and be an efficient electricity generator is hotter and it reduces the plant efficiency?
I love that question, Lisa. Thank you. Because we released a report 2 weeks ago that talks about this issue. And we're going to be releasing another report in another 2 weeks that goes a little bit more in depth. The point that we're making is that if you have a very severe, protracted, extended drought, like the drought we had in the 1950s, a couple years before my time, but when we look at paleoclimatic data, we know that Texas had long, protracted droughts in the 19th century, early 1700s, and also the late 16th century. But if you had a long, protracted drought that decreased the amount of water in your rivers, lakes, and reservoirs, that's going to present a challenge to the intake that a lot of your thermal generation needs, your coal, natural gas, and nuclear plants. The other issue is that you have like a smaller water body, and the discharge from that thermal plant goes back into the water source. If it's a hot summer and those waters are already warm, that discharge is going to be hot. And heat under the US Clean Water Act is actually pollution. And so that could substantively affect or impair some of these riparian ecosystems, opening up a whole new can of worms. Forgive me on not coming up with great metaphors after talking straight for 2 hours. But yeah. And so our point is like we need to talk as well about what can we do to improve our state's resilience to drought. And one of our major initiatives for next session is going to be on water policy, where we think we need to build a broad, diversified water supply portfolio that provides the water supplies not only for growing communities, but also make sure that growing industries as well, including our electric generation, has the water it needs to generate.
Well, good luck forcing the rain to fall, but it's
not.
And the
Whoever
problem
prayed
is,
for rain on was it Monday? They did a really darn good job because we got like we had no rain for 2 months, and then like
Yeah.
in 2 hours we got 2 months worth.
Right.
that's the problem. You have to look at the statistics of the rain, and the
Right.
problem is the big rain events with no rain in between is very difficult
yeah.
for our systems to well, it's very difficult to model too.
Well, it's consistent with the trends that we're seeing with regard to drought probability, is that it's a combination of hotter temperatures, increased average temperatures, more extreme temperatures, and this increased variability, which is precisely what you're describing there, Bill, where we have a lot of days of no rain, then a few days with tons of rain, biblical proportions of rain, and then lots of days of no rain. That variability in rainfall is certainly going to exacerbate and sometimes accelerate the drought conditions that we have.
Just a comment too. I've looked at another thing, which is solar energy on the roof, and Texas lists about 20th in the nation. And this goes back to Larry talking a little about normalizing data. Make sure you divide it by the population. And you look at the 5 leading states in the United States with rooftop solar are Hawaii, California, Massachusetts, Arizona, and Rhode Island. And it's kind of meaningless, I think, sometimes when we look at data and it's not normalized, because you have to consider the population or the size of those things, when you have data out there. So please be careful, I think, about that. Larry kind of pointed a little bit about that. So make sure your data is normalized.
I'm gonna go ahead and we've been dragging Jeremy out of actually what his model did tell us into all the other things that we love to talk about. And so, Jeremy, I really wanted to thank you and the Texas 2036 overall. The starting from data and being able to bring people into an agreement of what it is that we have in front of us and how to talk about it. There's lots of things the models don't do, but they do what they say they do, and they do them well. And so they make for a great discussion point. We certainly can't look past the, no matter how much people may like one or the other of the 4 primary models, which are really just illustrations to make comparisons. I mentioned earlier, the all of the above solution, not only does it track well with the best other possibilities for GDP growth, tax base, this, that, and the other, it points out, and that's kind of why I was picking on you a little bit on those last bullets, even the all of the above, just like when you said in the water that Texas 2036 is going into an aggressive, many-faceted water approach to both adequacy, resiliency, et cetera. Even an all of the above decision is a policy decision. And so, recognizing that, okay, I kind of like that model and it didn't call for, restrictions and handcuffs and choosing the winners, but oh, by the way, how do I make that one happen best? So those are the types of things you can bring to the legislature. You can bring to other parties that normally wouldn't have even started the conversation with you and say, well, okay, what are the parts of this that we like? So thank you very much. It was very informative, and really enjoyed the discussion today.
Thank you for having me. And I will share you a copy of the PDF of the slide deck this afternoon.
Thank you very much. We really appreciate it. Okay, I'm going to stop the recording now.
You can stop the recording. Go ahead.